Caroline, go
Thanks,
ahead.
Kristen. To start off with, I'd like to give you a little bit more background on why we are doing this. So the Process Study and Model Improvement Panel traditionally has offered the possibility to provide feedback to process studies at various stages throughout their lifetime. And the purpose of this has been twofold. On one hand, we like to provide feedbacks on plans and challenges that individual process studies might be facing. On the other hand, we'd also want to collect information and distill programmatic lessons more broadly from across process studies and field campaigns that could then be of benefit for current and future observational efforts. And this will hopefully help to meet the broader goals of improving understanding of physical processes in various different components of the climate system, and in particular how this then can be translated to improved modeling and observational capabilities. This year we've decided to make this effort that the PSMI panel has been doing for some time open more broadly to the community through this webinar series to showcase the efforts, achievements, and in particular also then challenges and by that these process studies are facing. On the other hand, we'd like to benefit from the expertise and feedback from the research community more broadly to provide us with feedback. And we'd also like to encourage a dialogue across a wider segment of researchers, potentially not just from those directly involved with process studies, but also from theory and modeling perspective. So that's the reasoning for these webinar series. We are very pleased to have our first speaker today, Professor Sarah Gilly from Scripps Oceanographic Institution. Sarah received a Bachelor of Science in Physics from Yale and a PhD in Physical Oceanography from the MIT Hui Joint Program. After doing postdocs at Scripps and the University of East Anglia and a faculty position at the University of California, she's been now at Scripps since 2000. And she'll be talking today about DIMES, the Diapycnal Isopycnal mixing experiment in the Southern Ocean. Thanks, Sarah.
Thanks. Excuse me. Thanks for the introduction. And I'm going to talk today about this very large field program, DIMES, that has been going since its inception as an idea for probably more than a decade. It's involved a very large number of PIs in the U.S. and the U.K., and so I think I drew the short straw to have to present on behalf of everyone. I'm certain to get things wrong, and I'm really glad to see that there's some DIMES investigators who've dialed in who will hopefully set me straight. So DIMES has been funded jointly by NSF in the U.S. and by NERC in the U.K. There's quite a bit of information on our website, dimes.ucsd.edu, so I encourage people who really want to track down more details about papers and publications to go there. The effort was conceived as a very broad effort with many components, and I'm going to talk through a lot of that today. It's been trained, in addition to the PIs, it's been trained a number of students and postdocs. I made an effort to list people here. I'm sure I've missed as many people as I've managed to include. So I'm going to work through the template that US CLIVAR sent me today, which first asked about the current status of DIMES. So as of now, DIMES has been going for a while. The proposal that was funded was submitted in 2006, and funding started in July 2007. The field work was carried out from 2009 to 2014. And so we're now at the tail end of analysis proposals. Proposals that were funded from 2012 to 2015 are in their no-cost extensions, and that's really where we are. So, so there's a lot of science that's come out of DIMES. If you really want to hear about the science and you've dialed in to try and get an update on DIMES science, this is probably not the right forum. You could get off the webinar and go look up the JPO Special Collection and the publication list on the DIMES website for further information. So um, the fact that we're in our final analysis stage for many of us means that what we're doing now is asking really broad questions about how to apply the ideas that have emerged from DIMES to ask about processes governing the entire Southern Ocean and, in fact, other parts of the ocean as well. So it's very much in a end of synthesis stage. We also have a lot of data that are still being looked at in a variety of ways. So DIMES from the beginning involved both observationalists and modelers, and the template asked about that. So I made an effort to sort people into observationalists and modelers. So this is just PIs. There are lots of students. And I've here color-coded people blue for the UK and red for the US, and tried to sort into observationalists and modelers. But I got stuck doing this, and I, in fact, didn't even manage to get Karen Haywood or myself sorted into a category, since neither of us went to sea, but neither of us is really a modeler either. The photo in the corner shows just some of the core seagoing work from DIMES. This is the tail end of the original tracer deployment on the first U.S. cruise. And so what you see on the left is the tracer deployment system coming out of the water, I think. So the original motivation for DIMES was really driven by asking about meridional overturning in the Southern Ocean. So the schematic here shows the meridional overturning as we tend to represent it, with water moving along isopycnals and upwelling into the Southern Ocean along this pathway, which I'm marking with green arrows, and then either returning northward through an upper cell or southward through a lower cell. What we knew going into DIMES is that this meridional overturning circulation depends enormously on how you think about the long isopycnal adiabatic mixing in the Southern Ocean. So if you look at global climate models, they're very sensitive to that the representation of that mixing, but there'd been very little effort to try and measure or characterize the processes responsible for that. At the same time, we realized that although most water mass transformation, most diapycnal mixing happens at the ocean surface, the Southern Ocean has an enormous amount of very rough topography, and that offered a pathway to potentially short-circuit the adiabatic route for overturning and transform water properties in the deep ocean. So DIMES was conceived to try and address both types of questions. The hypotheses going into DIMES were both that diapycnal mixing should be relatively small over smooth topography and increase over rough topography. And so the notion in DIMES was to start out by looking at the region upstream of Drake Passage, which I'm marking with green arrows here, where the seafloor is relatively flat, and there was an expectation there would be very low diapycnal mixing, very little internal wave generation that would lead to substantial vertical mixing in the ocean. And then to track water moving into Drake Passage, where the bathymetry is much rougher, which I'm showing here, and where we expected that there might be much more internal wave generation and much more mixing. At the same time, the hope was also to look at how isopycnal mixing works throughout this region, to observe how it, and to observe not only how it varies spatially, but also how it might vary with depth, depending on the flow relative to a critical layer, the depth at which the westward propagating eddies would move at the same speed as the eastward advection. So DIMES then was conceived with multiple components. It was really a three-ring circus. So a tracer release went in at the yellow star, shown right here. And So that went in the first U.S. cruise, which is marked in this box here. And then the the tracer, was subsequently resurveyed in annual cruises, and the timeline is shown going along this axis at the bottom. In addition to the tracer, a number of Isopycnal following Rafos floats, acoustically tracked floats, were deployed at the same time. So this was actually an enormous number of floats, about 180 in total, with sound sources indicated by these blue dots here. So these were acoustically tracked, which gives a continuous position in contrast with Argo floats. Then in subsequent cruises, the tracer was surveyed to figure out how it had moved, both vertically and horizontally, and at the same time microstructure surveys were carried out to look at direct measures of turbulent mixing throughout the water column. The UK component of DIMES also involved a mooring array, centered at this blue star here. And from the outset, there was quite a bit of modeling, both on a global scale and in process study form, both on the US and UK ends of the project. So here's an example of some of the data that have emerged from DIMES. This is showing at the top the floats that were deployed as part of DIMES. So these are the real floats. And in the bottom panel, numerical simulations of floats. And the hope has been, although 180 floats is an enormous number, it's easy to find gaps in what a finite number of floats can do. And so the hope has been to show that the statistics of numerical floats resemble the statistics of real floats, and then to use them together to interpret along isopycnal diffusive or dispersive processes in the ocean. So I'm going to talk a little about the interpretation of the isopycnal diffusivity in the ocean. This is an analysis that Tulloch et al. Published in JPO. And what it shows in the as a function of depth is in the blue dot, the eddy diffusivity inferred from the DIMES tracer. So I showed you floats before, but this is from the tracer. And then that's compared with results from numerical simulations. So there's another value here with an error bar, which comes from an ensemble of numerical simulations, and then the black line represents a vertical profile of tracer diffusivity within the numerical model. And what this has shown is that the model is quite successful at reproducing what we can infer from the data. Maybe surprisingly successful given the uncertainties in the data. And the model, this particular model, implies quite a substantial vertical structure with higher diffusivity at mid-depths and less in the top and bottom. Overall, the isopycnal component of DIMES has shown that the floats and model simulations provide a very consistent estimate of effective eddy diffusivity on the order of 800 plus or minus 200 meters squared per second for the region upstream of Drake Passage. So this is shown here for the floats, indicating the effective diffusivity. There are a number of open questions that emerge from the isopycnal component of the DIMES study. One is that although the region upstream of Drake Passage, which has flat topography and relatively laminar flow, is easy to characterize, everything falls apart when you move into Drake Passage, and the streamlines of the Antarctic Circumpolar Current swing substantially northward. So we're still left with the question, how do we really characterize eddy mixing in Drake Passage, where the mixing is likely to be substantially larger than it is upstream of Drake Passage? The results that I just showed imply a very clear vertical structure for eddy diffusivity, but different modeling studies have led to different inferences about the vertical structure of eddy stirring, and that's still very much an open question, how to infer vertical structure and how robust it is, especially in places where mixing is more difficult to characterize. And then finally, if we're thinking about moving from process studies to model improvement, you might ask, how much we can use this information that we've gleaned about eddy diffusivity to lead to better or more robust numerical models on a climate scale. And I think that's still very much an open question. We continually find that parameterizing eddies is a challenging problem. The Diapycnal mixing component has a different set of questions that have emerged here. I'm showing just a sample of results showing very much what DIMES initially inferred. This is from EM apex floats deployed by James Gerton, showing shear spectra and vertical diffusivities estimated for two regions. The blue region is in the Southeast Pacific, and the red is in Drake Passage in the Scotia Sea. And what you see is that there's, in the diffusivities, more than an order of magnitude difference between the two curves. So there's substantially more mixing inferred throughout the water column in the Drake Passage area than there is in the more quiescent, flat-bottomed Southeast Pacific. The yellow star shows what the tracer had done after a year, so when it was still in the Southeast Pacific, and it's a pretty good match with the EM apex results. Overall, the tracer shows very similar results, so this is summarizing the tracer surveys. Here you can see a map of the tracer surveys going from cruise A to B to C with different dates. And what you see is that in the initial cruises upstream of Drake Passage, the tracer is gradually dispersing, but over a fairly narrow depth range or density range. And then suddenly, as we get to these blue and yellow lines, the surveys, the tracer have moved well into Drake Passage through the rough topography, and these curves indicating where tracer is found have suddenly spread much more rapidly, indicating a much more rapid vertical mixing in this rough-bottomed topography. So we see an order of magnitude difference in mixing from the abyssal plain to this Phoenix Ridge, Drake Passage area and beyond, with clear evidence for enhanced mixing near the bottom. And this has led to a number of open questions. What sets the Diapycnal mixing? To what extent do topography, current speed, and other processes matter? And there's clear evidence that as the tracer moves along the northern edge of Drake Passage and it's scraping along the bottom, it may undergo more rapid mixing than it does if it's in deeper water. And then we've seen a lot of evidence for what happens in the deep ocean from the DIMES data, but what happens in the upper ocean, and how does wind drive mixing? There are very strong winds in the region, but it's hard to see the response to a single wind event from one cruise. So that's a quick summary of the science, and then I'm going to talk through some of the more logistical issues that emerge from the results. However, I see that there's a question here. How well is the kink at 1.5 kilometers resolved vertically by observations? And the answer is, this is the kink here at 1.5 kilometers, I think. Is that right? And the answer is that it's not resolved by observations, because this would have required us to have substantial numbers of floats at two different levels, or tracer at two levels, and that was not available. No, not this one, the one in the following slide. Okay. One more, this one. This kink. Okay, I don't know the answer to that, but James Gerton's on the line, so maybe he can answer that.
Let me see. James is on the line. We've got a couple phone numbers that he may be dialed in, number 206 or 609, do you think, Sarah? Do you know where he's coming from?
I don't know if he's just online.
Yeah, so maybe he is tuned in with audio. James, if you can send me a chat with your phone number, because I don't see your audio connected for your phone, so I can't. Thank you. Okay, let me unmute you. Great, you're unmuted. Go ahead.
Yeah, I think you know that that kink at the bottom there in the EM apex data, that's shear measurements, and I think below 1,500 meters we definitely did have less data. Most of the floats were profiling to above that kink, so there's a bit more spread in there. So I would say that the increase with depth is probably robust, but that kink is probably not. So if that's enough of an answer.
Gidon, did this answer? Yes, it did. Thank you.
Okay, thanks.
Thanks.
Okay, moving on then. So then what we need to do now is talk about some of the practical implementation issues that PISMIP has specifically asked about. So one is about analysis and modeling. And I'm just going to address the U.S. efforts, but there's also an enormous amount of UK analysis and modeling, so this is just in the interest of time. But U.S. efforts have made very extensive use of modeling, both from the beginning. We worked with the POP model that came out of Los Alamos. So Matt Maltry put floats in it many years ago, more than 10 years ago, which were used to plan the initial experiment to look at how rapidly tracer might move and how it might disperse. And then the POP model was used extensively throughout the program, both to evaluate likely uncertainties in the project and more recently to assess the hypotheses that there could be vertical structure in the eddy diffusivity and to look at critical layer depth effects. In addition, a lot of work has been done with more idealized models. So I think ideas based on geoids plus altimetry in a very idealized framework. Andreas Klocker concluded from those sorts of studies that although 180 floats was nice, it would really be much better to have 1 million. So we've been puzzling over how to tell the program managers that. And then there's been a lot of regional modeling. Some of the results I just showed were from work that Ross Pollock initiated using a regional version of the MIT GCM to really look at high-resolution processes in the Drake Passage region. And as we've continued analysis into the final stages, we've been working quite a bit with the Southern Ocean state estimates. So that's an assimilating model that's constrained to observations throughout the Southern Ocean. And we've used that with particle advection and tracer releases to look closely at how water moves not only through the Drake Passage region, but also more broadly through the full Southern Ocean. The template I was given asked about expected contributions to sustained observations. And my initial reaction to this was to think DIMES was a process study with no plans to build sustained observations. But on further reflection and with prodding from other people, James Girton pointed out that DIMES has led to development of the EM Apex float platform and to data product development, which together have led to a lot more work in Antarctic margins and a growing international interest in both process studies and sustained observations in the region. So I think although DIMES is very much a process study at its heart, it's had a potential impact that extends beyond just the DIMES field study. And then we were asked what helped integrate modeling and observations. And so I want to address this separately for isopycnal processes and for diapycnal processes. For isopycnal processes, since observations are sparse, modeling has been enormously beneficial for planning, interpretation, and assimilation. But I'd say that really doing an integrated assessment of the data using models and observations takes time, and it's been surprising to me to realize just how many years it takes for us to have the models in order so that we believe the model results and we believe the data and we're able to interpret them together. And that finally is happening, and a couple of papers have been submitted in the last few months that really do bring together, at least from my group, that bring together model results and observations in a very unified way. To make this happen, it's been really important that we've had annual meetings. We've taken advantage of some telecons at stages when that seemed helpful, and that we've allowed time to get the collaborative work to come to fruition. For the Diapycnal work, modeling is really challenging because the vertical resolution that's required to assess diapycnal variability is very high, and it's difficult to achieve that in the large-scale models we use for other purposes. So I feel like we're not quite there yet, although the work is beginning, and there's a lot of discussion that will take people into a point where it's possible to use models and observations in a more integrated way. It's just hard to get tidal forcing and internal wave generation with many vertical levels into a model that can be run over a large domain. So we were asked about difficulties, scientific, administrative, or otherwise, and I want to emphasize that on the whole, DIMES has been enormously successful. It's brought together a lot of researchers and a lot of science in a very collaborative way, and it's delivered results that really have told us address the hypotheses we set out to address. But there have been numerous challenges, many beyond our control. So the background picture shows a perhaps not atypical view of the ship in the Southern Ocean with an enormous amount of spray and wave activity. It's difficult to work in the Southern Ocean. It's a remote area. It has severe weather. DIMES had multiple medical evacuations. The US-2 cruise suffered tragically the death of the captain of the ship, which involved quite a bit of reorganization. There have been ship breakdowns and ship repairs. From the outset, the tracer that was used was a new tracer, and the supplier had difficulty manufacturing it. So there was too little tracer, and there was concern that it would be difficult to track. That proved not to be a problem. Some of the floats initially had ballasting problems and involved a little bit of scrambling to get them replaced. And the Hui microstructure profiler was lost on one of the last cruises. So all of this has been stuff that just happens, I would say. On shore, we've also encountered problems. Because this is a UK-US collaborative project, we discovered all sorts of difficulties with visas that make it challenging to bring people together. And there were people both based in the US and the UK who had difficulty getting to meetings. That might lead you to say that we should be switching projects like this to work more with webinars, but I think we did gain from in-person meetings when people were able to get to the meetings. So DIMES' successes overall are really a testament to resilience, that people have been able to work through these minor problems and bring science out of the results. We were asked about coordination between agencies, and in this case, the coordination was largely between the US and the UK, and so I put this figure back up because it nicely shows the scheduling for 11 cruises alternating between US and UK ships. I think that coordination was handled largely by the PIs who led the cruises, keeping track of what was going on. So that, to me, never appeared to be a major problem, and we were fortunate, even in the initial proposal, that the US and UK funding agencies were willing to consider this as a joint project. And then we come to data sharing. So the data sharing for DIMES has been handled by CCHDO, the CLIVAR Carbon Hydrographic Data Office, which is based at Scripps. Here I'm showing a screenshot of the data page for the first cruise, the US-1 cruise. And you can go to this through the DIMES website and find the data, and they've been made public. So this is the way things are supposed to work. There have been challenges to data management for the DIMES project. In particular, many of the data requirements have been relatively new, or the way they've been implemented has been relatively new through the course of DIMES. And so PIs have been unsure what they had to do. And in some cases, especially for the more recent cruises, people are still working on reporting data. Because this is a UK and US project, the two countries have different specific data management requirements. So the UK data is supposed to go to BODC, the US data is supposed to go to CCHDO, and ultimately NODC, or their newly named acronym. And And so getting all the data into one place has involved some coordination between CCHDO and BODC to try and make sure that nobody's toes are getting stepped on and that the data are being made available. And perhaps the most challenging aspect for DIMES has been that it involves a number of unconventional data types, at least for CCHDO, which deals largely with hydrographic data. So DIMES has quite a bit of microstructure and tracer data, and neither of those has had a standard data format available internationally. It has a lot of float data. It has, although CTD and XCTD data are fairly routine, in this case data were co-located with some microstructure data, and there are questions about how to make all of that jointly available. There are the EM-APEX floats, and there is an enormous amount of model output, where we've had to decide how much needs to be made public and how to do that. So I think there have been a lot of successes in the data management. With microstructure data, which is really a new quantity to try and get into any data management structure, we spent a bit of time within DIMES discussing what to do, but ultimately made a decision that the turbulent mixing CPT that Jen McKinnon has led should take the lead on defining requirements. And so we pushed the job to them, and they did a great job. And that was also working with the CCHDO, so there was a clear push for CF-compliant NetCDF files that would be easy to work with. We were successful in implementing a password-protected data management system, which has allowed data sharing between the DIMES researchers prior to official release. And so that's been fairly successful. I think we've had more trouble getting to the point where we're sure the data were supposed to go public and getting them all publicly released. And CCHDO, because they do a lot of data management, has really thought carefully about how to implement the data management system for DIMES and to make it seamless and easy to integrate with other hydrographic data that they also manage. So they've run a very new and well-updated website for a web interface to make data available. And then finally, I'm just about to wrap up, but in the email exchange prior to this webinar, the DIMES investigators asked questions about this. What's emerging from DIMES? What should happen with the science emerging from DIMES? And in particular, we said, given that we're going to talk to PISMIP, there are some obvious questions. Should DIMES results lead directly to the establishment of a CPT? And so we've been discussing this for years at DIMES meetings, and the answer has been that it's not obvious. DIMES is an international project, and CPTs are US-based, so there's a mismatch there. And DIMES has had a strong modeling component from the beginning, so a lot of the things that you might do as a first pass have happened within DIMES. But DIMES has very interesting results both in the Isopycnal and Diapycnal components, and it would make sense to coordinate some of this with other process studies and to have DIMES results feed into a CPT ultimately. And maybe the more relevant question is, should DIMES results guide future process studies? And there, I think we've said undoubtedly. James Girton emailed me that DIMES was simultaneously too big for resolving detailed mixing processes and too small for capturing integrated Southern Ocean mixing, meaning that there's a lot of room to address all the scales in further process studies. So there really are themes that emerged from our email discussion, which focus largely on topographically generated effects. On the Diapycnal end of things, topographically generated turbulence and topographic lee waves and their impact on mixing have emerged as very important processes that haven't yet been studied. They were touched on in the DIMES observations, but there hasn't been a good effort to really understand the underlying physical processes. And on the Isopycnal side, there's emerging interest in topographic stress, topographic barriers, and the role that topography plays in non-local mixing and spatially varying lateral mixing. So together that leaves a lot of questions open that people would like to see addressed in the future. So I'm going to stop there. Thank you very much, and I'm happy to have a broad discussion.